this part almost 15 minutes because the first part is almost 10 minutes 49 seconds. So I make it next part 2. I will make part 2 because having any mic issue. So
If you change your mind,
I
I'm here whenever you want to chat again.
I repeat this. I have a mic issue, so I resolved it. So let's start my Maya. So Maya, my next question from you is: can a magnet lose its magnetism, and what is attraction and repulsion? Please give me a very interesting answer on this topic. So let's start with answer, Maya.
Good question. Magnets absolutely can lose their magnetism. It's not like they stay magnetic forever. There are a few ways this can happen. Heat's a big one. When you heat a magnet up enough, that heat energy can actually disrupt the alignment of all those tiny atomic magnets inside it. It's like shaking up a neat arrangement, causing them to become more random again and weakening the overall magnetic field. Another way magnets can lose their strength is if they get dropped or hit hard. Physical shock can also mess up that internal alignment. What's really interesting is there's something called the Curie temperature for each magnetic material. If you heat it past that point, the magnet loses magnetism entirely and stays demagnetized. Another thing that can happen over time is natural demagnetization, where the magnetic poles slowly weaken until the magnet can no longer perform its magnetic field, like magnetic forces, attraction, and repulsion. Now, for attraction and repulsion, attraction is when opposite poles, north and south, pull towards each other. They're drawn together because their magnetic fields work together, making that magnetic connection stronger. Think of it like opposites completing each other. Repulsion is the opposite. It's when like poles, north and north or south and south, push away from each other. Their magnetic fields conflict, creating that force that separates them. It's kind of like two objects that don't want to share space. Together, attraction and repulsion are fundamental properties of magnetism. They show how magnetic forces create the interaction of magnetic fields within matter. Both are part of the same magnetic force but act in opposite ways, resulting in magnetic interactions we can observe daily. That was a pretty in-depth
Wow,
answer. Anything specific
I
about
really
that you'd
like it.
like
Your
me to
answer.
clarify or dig deeper into?
So, which materials are attracted to magnets, and why
Awesome!
is iron magnetic? So, please give me a very interesting answer on this question. So, let's start your answer, Maya.
Glad you liked the last answer. Now let's talk about which materials hang out with magnets and why iron specifically is magnetic. So, what gets attracted to magnets? Mainly iron, nickel, and cobalt are drawn in, plus some other alloys, things like steel, which is mostly iron. But the key here is that these are ferromagnetic materials, meaning they can become magnetized. What about other metals? Aluminum, copper, gold, silver. They just don't have the right atomic structure to line up their internal magnetic field, so magnets don't really stick. But it gets a bit more nuanced because some materials react weakly to magnetic fields even if they don't get pulled in, like bismuth or water. It's more of a faint push-pull rather than a strong attraction. Now, why is iron special? It all comes down to what's happening at the atomic level within iron. Iron has this unique arrangement of electrons in its atoms. Specifically, its electron configuration makes it easy for those electrons to align their spins, creating that magnetic field we talked about. These alignment spins allow magnetic force to generate powerful attraction and alignment. The reason being, their electron arrangement makes it easier for their individual magnetic needles to coordinate. In fact, iron is one of the most efficient at setting up this magnetic alignment, which is why it's such a workhorse for magnets and electromagnets. The iron atoms can easily be magnetized, which allows them to create a magnetic field that will stay that way without getting random magnetic force direction. It's just a perfect match for magnetism, the right electrons in the right atomic structure. That's what makes iron so magnetic, while materials like aluminum or copper can't really pull off the same trick. Does
Okay,
that explanation of
that's
why
really
iron
great,
is
Maya.
magnetic
I
make
really appreciate your answer and you give me a very
You're very
interesting answer.
welcome.
Are all metal magnetic? What happens when a magnet touches plastic or wood? So please give me a very interesting answer on this topic and very answer and very insightfully answers. Let's start your answer, Maya.
Glad you're finding the answers interesting. Okay, so what happens when you try to get a magnet cozy with plastic or wood? Not much, honestly. You won't feel a magnetic pull. Here's the thing. Plastic and wood are what we call non-magnetic materials. Their atomic structures just don't have those electron arrangements that respond to the magnetic field we talked about earlier. Remember, magnetism relies on having those electrons spinning in alignment. Both plastic and wood are mostly made of atoms that simply don't work that way. Now, here's where it gets a little subtle. They aren't completely oblivious to magnetism. You can technically induce a super, super tiny bit of magnetism in them if you really cram the magnetic field at them, but it's so weak you can't feel it. Wood's electrical composition and atomic structure don't engage in magnetic alignment, so it can't sustain magnetism, while plastic composition contains polymer chains that aren't compatible with magnetism. Basically, their atoms are made of elements that just don't have the electrons in the right configurations for magnetic alignment. So magnets pretty much ignore them. They pass right through each other without anything really happening because there's no magnetic response from the material itself. Pretty simple, really. Clear enough on that one?
Okay, so Maya, my next question from you is that how can we test if an object is magnetic and what is magnetic field? Please give me a very interesting answer on this topic. So let's start your answer, Maya.
Okay, let's dive into testing magnetism and magnetic fields. The simplest way to see if something's magnetic is pretty straightforward. Just bring a magnet near it. If the magnet sticks to the object, or if you feel that pull, it's magnetic, or at least has some magnetic elements in it. You could also try dangling the magnet from a string. If it swings towards the object, there's attraction happening. But you can get more scientific too. You can use iron filings to see what they stick to when you sprinkle them around a magnet. The filings only line up and stick along where the magnet's force field is actually working. Now, for magnetic fields, imagine invisible lines stretching out from every magnet, connecting north to south. That invisible pattern all around the magnet, where its force works, that's the magnetic field. The stronger the magnet, the more concentrated those lines are. They push harder on other magnetic objects. Fun fact, even space has magnetic fields created by planets, stars, and everything that creates magnetic fields. The most noticeable effect of Earth's magnetic field is that it shields us from dangerous charged particles shooting from the sun. What's really mind-bending is magnetic fields aren't just from magnets. Electrical currents create them too, and that's key to electromagnets. Magnetic fields are also there, even if you can't see them. They can move things without touching them, which might seem like magic, but it's just science. So, to summarize, a magnetic field is the area where a magnet's force exerts.
Okay, so Maya, my next question from you is: can we see a magnetic field, and how do iron filling shows magnetic fields? Please give me a very interesting answer on this topic. So let's start your answer, Maya.
Good question. You can't actually see a magnetic field with your naked eye, it's invisible. But we can visualize it using iron filings. When you sprinkle iron filings around a magnet, they don't just randomly scatter. They line up along the magnetic field lines, those invisible paths where the magnetic force works. Each tiny iron filing becomes like a miniature compass, aligning with the field direction at that spot. What happens is each filing becomes temporarily magnetized by the bigger magnet and then clings to each other. The iron filings show the shape of the field lines. You'll see patterns of curved lines spreading out from the North Pole and going into the South Pole. If you had some colored filings or some other means of showing alignment, the way the iron filings arrange shows the whole field structure. It's almost like you're mapping out the invisible landscape of magnetic force. The more iron filings, the better. The visualization of the invisible
Okay,
landscape, because they create
I did
enough
answer.
of an alignment for the viewer to understand what's happening with magnetic field lines. That's why it's such a classic way to visualize them. It makes the invisible field visible and shows exactly how magnetic force works in a given space. Does that make sense about how iron filings reveal magnetic fields? Take your time, no rush.
Okay, that's really great. I really appreciate your answer, Maya. So, how far can magnetic force act? What shape is magnetic field? So, please give me a very interesting answer on this topic. So, let's start your answer, Maya. I'm waiting for your interesting answer.
You're asking about range and shape. Great questions. Magnetic force technically reaches infinitely far, but it weakens with distance pretty quickly. The farther you get from a magnet, the weaker. Imagine shouting really loudly. Someone nearby hears it clearly, but by the time it reaches across a football field, it's barely audible, right? Magnetic force works like that. There's no absolute distance where it just stops working entirely. The intensity just gets so weak it can't affect things anymore. As for the shape, magnetic fields generally have a dipole shape, meaning there's like every magnet has north and south poles. If you picture the field lines, they emerge from the North Pole, curve around, and go back into the South Pole, creating these looping, symmetrical patterns. What's really interesting is it's 3D. Those field lines wrap around the magnet like invisible bubble patterns in all directions, not just a flat shape. The field can become more complex with irregular shaped magnets, but it's still essentially following that dipolar pattern with the field spreading outwards from the poles in all directions around it. The strength and density of the lines show how strong the field is at any specific point around the magnet.
Okay, so my next
That
question from
covers
you is
the
that
range and
Maya,
shape. Make
uh,
sense?
please give me answer. What is the? This is my last question. What is the difference between permanent magnets and temporary magnets? What is electromagnet? Please give me a very interesting answer on this topic. So let's start your answer, Maya.
Absolutely. Let's wrap this up with permanent versus temporary magnets and electromagnets. Okay, permanent magnets are what you probably think of when you picture a magnet. Think fridge magnets, compass needles, stuff like that. These stay magnetic pretty much forever because their atomic alignment is locked into place. They're made from ferromagnetic materials that have a structural arrangement where atomic dipoles stay stable. It's like building with Legos that keep holding their shape. Temporary magnets, on the other hand, only stay magnetic when they're close to a permanent magnet. or magnetic field. Like when you bring that magnet near an iron nail, it becomes temporarily magnetic, but when you remove that magnet, the nail loses its magnetism. Temporary magnets don't stay aligned on their own. Finally, these are created when you run electricity through a wire coil. It creates a magnetic field that only exists while current flows through the coil. The really cool thing is you can control the strength of an electromagnet by changing the voltage or number of turns in the coil. So you can turn magnetism on or off and adjust the intensity. Unlike permanent magnets, which are always magnetic, even when current isn't running through them.
Okay, so this was our Maya. Next part, 15 minutes completed. So this was our Maya. I hope you like it. I'll meet with you, Maya, next
Hey, are you
topic.
still there?
Take care.